Well, good morning dear and welcome back. So we are trying to understand how support vector machine works by developing the model from the very fundamental. Okay. So meanwhile, recapitulation, support vector machine is a binary linear classifier which is developed using the analytical method. Basically, the classification problem has been modeled as a constant quadratic optimization problem. Okay. And basic idea was so that my classifier or divider, okay, which is discriminating between the two classes, will make a maximum margin from both the classes, so that misclassification rate will be reduced and more accurate prediction will be there, okay, compared to all other classifiers could not guarantee that always the decision boundary will maintain a maximum margin from the classes. Okay, they may for some combinations of your values of W which you might by accident by some trick you may discover, but it is not the inherent property of those classifiers which will guarantee that this decision boundary will maintain a maximum margin from both the classes. But this support vector machine, they have that. Okay, so support vector machine model we are trying to understand. So we are developing a model. Okay, so you see here we are considering two classes. Say negative class. So this is negative class. This is positive class. This samples I am considering positive class. This samples I am considering negative class. So I have two classes, minus 1 and plus 1. Okay, these are the two classes which we are considering. Here is my parameter, model parameter W. Okay, and say I have an arbitrary sample point here, which is denoted by a position vector V. Meanwhile, these are the two features x1, x2. This is extremely simple diagram we are considering so that we can understand the intricate detail. Okay, and say this is any arbitrary point whose position vector is V. So we are interested to actually classify by computing this dot product between these two vectors and making it greater than or equal to k, where k is an arbitrary constant. Say, okay. And the constant value I do not know. I will have to know that value because this is very intuitive. You see, k value should be such that it should be the dot product should be able to classify. You see how? Just I can write down this plus b, okay, greater than or equal to 0, assuming k equal to minus b. K is a constant, b is also a constant. So I have assumed that k is minus b. So this is what we are getting. So you see, if now this dot product greater than or equal to 0, then my classifier will decide then positive sample. And if it is less than or equal to 0, then it's negative sample. So right now I can write also goes to confusion. Then less than, because 0 less greater than equal to 0, they will be classified as positive sample. So it is good technically to write less than 0, then they belong to the negative class. So if we could represent any sample by a vector and make a dot product with another vector which is supposed to be maintaining a normal angle, 90-degree angle with the structure, then this structure, with the help of this structure, I can, by selecting suitable value for B, I can classify. So this is very simple concept, right? Classify between positive and negative samples. Okay. But the problem is we do not yet know either double vector or bias. B is called incidentally bias. So we do not know either of these parameters. And by formulating this problem as an optimization problem, and by formulating constraint, we will try to find out these two parameters. So that is the basic objectives. First, we create constraint. You see, right now this is all free. Okay, the W, B, I do not know what are the values. Okay, so if W values are actually, what is the W value proper, so that it will really work to classify, we are going to find that, right? And what is the constraint? We are writing, say, take a sample from, as for example, take a sample from positive class. Okay, so it is from positive class, and call it sample, we say S is a vector again. In support vector, everything is vector, right? Okay. So W is also a vector. So now V was arbitrary. Now in terms of sample, this is a sample, positive sample, okay, plus B. Is it incidental? This is called decision rule. And we are calling it, very important, equation 1, equation 1. Okay. So that is actually greater than or equal to 1, because all positive sample is considered as plus 1. Okay. So take a sample and then we are rewriting this constant equation in this form. So this will be valid for any, this constraint will be valid for any positive samples, right? If the samples need to belong to a class 1, then this is the constraint which has to be obeyed always. Now take a sample from negative class. Say this is negative vector represented by S I am using, because samples are support vectors. Assuming that we do not know what is support vector yet, so just S I am writing. So then W dot. So V is now characterized by this vector. less than equal to, so this is, let us call 2, equation number 2, this is called equation number 3. Now you see this 2 and 3, I would like to fuse them together for mathematical convenience. Fusing, I do not want to write two equations in equations for constraint, but we will write an equation which will represent both the equation in one form, fusing 2 and 3. By introducing a parameter, say yi, such that yi equals to plus 1 for positive samples, equal to minus 1 for negative samples. Okay. So then the equations in a combined form can be written. So this is constant equation. Plus b greater than equal to 1. You see? For negatives, both are represented by this 1 in equation. Because for negative sample, this will be this, and this will be minus 1. So directly for negative sample, you will get this from here. For positive sample, again, from positive sample, you will get this if you put y equal to 1 and this equal to s positive. Agree? Or I can write down plus b minus 1 equals to 0 for samples on the order. And this is my constant equation, say equation number 4. So you see, this one has been taken over here, and now we are, that's why this is perfectly okay if I write less than equal to 1. Here also we could write less than equal to 0. Because now whoever is actually 0, they belong, they may not belong to any class, but they can belong on the order. Okay. For this, at the boundary of positive class, at the boundary of the negative class, those samples, when they are on the order, they must obey this constraint. So this constraint is a benchmark. Okay. So if you want to be a support vector, that means support vector are those vectors which is supporting the structure, as I told you, that they must be at the boundary of each classes. So if you want to be a support vector, then you must follow this constraint. Okay. Now let us try to move forward and try to calculate the width of the gutter. Okay. So here, same drawing I am again. Let us draw. Okay. So this is say this is my origin, and everything is a vector here. Okay. So this is my negative class. say, and this is positive plus. So y equal to plus 1, y equal to minus 1 from these samples. Okay. And let us now demarcate. So this is say this point is A. Okay. And say this is point B. Okay. So I want to determine the width of the gutter of the structure. Okay. So I am writing. Drawing W, which is a vector which is perpendicular to this gutter, okay, perpendicular to say this line. Okay. I can call it C, AC line. Okay. Fine. So what will be the width of this gutter in terms of my parameter W? Let us try to understand. I can write from triangle's law of vector, A plus AB equals to OB. Correct? Now, so what is AB? AB will be OB minus OA. So OB is actually what in terms of support vector? So this is vector plus minus OA. OA is negative support vector. Okay. So this is A. Now width of this gutter is a perpendicular distance, that means it must be in the direction of W. So if I can figure out a unit vector in the direction of W, okay, that is norm, then if I make the dot product, so width of the gutter, geometrically you can see very clearly of the gutter equals to AB dot unit vector, which is nothing but vector divided by its magnitude. Okay, this is the magnitude of W vector. So this is very interesting to know. Now you know what AB is. So the width of the gutter will be equals to, in terms of support vectors, so far you are with me, right? Say if you want everything to the mark, we are marking it as equation 5. Okay. Now, from equation number 4, that is very important equation, constant equation. Okay, equation number 4. Okay. What we are getting? For positive sample, positive dot W plus B minus 1 equal to 0. So that is giving you dot W equals to 1 minus B. Okay. And we can call it 5a. Then for negative samples, again equation 4 will give me that so negative sample this will be minus b minus 1 equal to 0. Just try to see. For negative sample this is minus 1. Okay, so this is minus, this is a minus because this is minus 1, this is minus. Okay. So this is what you are getting. So minus of this is equals to 1 plus b. Say this is 5b. Okay. Now from equation 5, using 5a and 5b, which we can get, I will just this times this, I will put a minus b, minus this dot this, that means instead of this, I will put 1 plus b, okay, divided by 1 by okay. So this is equals to 2 by okay. This is say I can get down equation number 5c. So we have got what we have got width of the gutter. So our task is objective. What is the objective? To maximize the width of the gutter. Okay. So if we are giving training samples, then we will try to fix our support vector so as to maximize the width of the gutter. That means to maximize the width of the gutter, that means to maximize 2 by W. Okay. Now, this is again mathematical convenience. Okay. Maximizing this term equivalent to minimizing 1 by 2 by equals to half W. Now, for mathematical convenience again is equivalent to minimizing W square. Okay. So, why we did this? And I will must be knowing because, as I told you, support vector machine is modeled as a constraint quadratic optimization problem, and for optimization problem we need to have an objective function. So objective function is now half W square, which is a quadratic function. Okay, as simple as this. So we have ended up from very simple geometry that our objective is to minimize half W square. W is the parameter which is defined here. And if I can do that, then given an example, the daughter width will be maximum. So we'll start from here in the next class and completely formulate the classification problem as a constraint quadratic optimization problem, and then we'll solve it. Okay. Thank you for your attention. Stay safe. Bye bye.